Okay, hello everybody. This is once again an additional extra lecture, and in this lecture, we will be dealing with moment of inertia of solid objects. So, this lecture is solely devoted to this topic, finding moment of inertia of some standard solid objects. So, these are very important from the perspective of your RTU examination, since the derivation of any one of these can come in your syllabus. So, let's start with the first one. Let me put the heading of today's topic here. It's moment of inertia of solid bodies. The first body that we will be taking is a thin solid rod of mass m and length capital L. In order to accomplish the complete derivation successfully, you also need to take some additional parameters. And especially since we are dealing with solid bodies, the concept of mass density will always appear in all derivations. So let me just take a thin rod which is L meters long. So this is the thin rod, and we have to find the moment of inertia of the thin rod about the centroidal y axis. So the overall length of the rod is capital L. The overall mass is given as capital M. Let us assume that the mass density means mass per unit volume of the rod is rho. Apart from that, you can see that the cross sectional area, this hatched portion, this is constant throughout the length of the rod. So let us also consider the cross section area as a constant quantity, capital A. Okay. Now, in order to find out the moment of inertia of any complete solid body, the approach that we'll be selecting is exactly similar to the first principle. And in first principle, what we do is we select an infinitesimally small piece, find its moment of inertia, and then perform integration over the entire body to find the overall moment of inertia. This is how we have already used the first principle for finding moment of inertia of areas. Now we will be doing that for solid objects. So let us learn with each step, and once you have practiced all these derivations on your own, you will be pretty much confident to reproduce all these derivations whenever asked in your examination. Okay, so moving on, these are the constant quantities. The first thing that you should do is list out the constant quantities that you have either assumed or they are given in the problem. So mass is the overall mass, M, capital M is the overall mass of the rod, rho is the mass density. If it is not given in the problem, you assume it as rho. But you have to include the value or the parameter of rho in your problem. Capital A is the constant cross-sectional area of the rod, and capital L is the overall length of the rod. And we have to find the moment of inertia about y axis, or in other words, the task is simply put what is Iyy of the entire rod. Now what we are going to do is, let us take a small piece of the rod like this. So I'm taking a small piece of the rod like this. And let us say the length of the small piece, since the length of the rod is aligned along the x direction, so let me take the length of this small piece as dx, and I am going to declare that the mass of this small piece that I have cut is very small and equal to dm. So this is the step that you have to take in every such derivation. So you draw the solid object, and appropriately you have to select a small dm mass or a small piece mass, for which you will first find the inertia and then you will integrate to find the inertia of the entire object. So once again, let us say that the center of gravity of the small piece is somewhere around here, and let us say that the distance of the center of gravity from our desired axis is x. So the small piece is at a distance of x. Now, can I write that the overall mass of the rod is equal to density of the rod multiplied by capital A into L? How is this possible? Because capital A into L is nothing but the entire volume of the rod. Now, if you multiply the entire volume with the density, you get the entire mass of the rod. So this is one thing, one relationship that we already know about the rod. Now, can we get a similar relationship for dm also? Since dm is the mass of this small piece, and let me just draw this small piece for you by taking it outside. This is the small piece. Now you see that the small piece also has a cross-sectional area of A. It has a length of dx. So the volume of the cross section of this small piece becomes A into dx. And since it is cut from the same rod, so it has the same density as that of the rod. So density multiplied by volume is equal to the small mass dm. So in other words, I can simply say that dm can be written as rho multiplied by a into dx. Now see what I'm going to do. If I look at the axis which is given to me and the location of the small mass dm, I see that this is at a distance of x from the axis. So if I want to find out what will be the small moment of inertia di for the small mass dm at a distance of x, then I can consider this small mass not to be in the form of a cylinder like this, but to be actually a point mass. So if I have a point mass dm at a distance of x from an axis, then I can simply say that the moment of inertia di will be dm into x square, according to the concept of moment of inertia. Now, what I will do is, since the small mass element dm has a moment of inertia equal to dm into x square, I can simply say that the overall moment of inertia of the complete rod about the y axis will nothing be but integration performed over the entire mass of di. So di I already know, it is this. Now I want complete I. So what I have to do is, since di is for a small mass dm, so I will be obtained by the integration of di for the complete mass, or if you are more convenient with writing it as capital M. So you have to perform the integration over the entire mass M of the body. So I will substitute this value here, and this becomes integration over mass of x square dm. Now we already have an expression of dm over here. Dm is equal to rho a dx. So this is what we are going to substitute here. So I will use rho a dx instead of dm here. So this becomes equal to, this integral is integral rho a dx. This is your dm. Okay, rho a dx is your dm. So I have replaced dm with rho a dx, and now what remains is x square. So I will put x square here. But now observe what has happened. Earlier, dm was the variable, or m was the variable of integration. But after replacing dm with this quantity, now dx or x is the variable of integration. So earlier when dm was here, then integration was over the mass. But now since it is dx here, the integration has to be performed for the entire length of the rod ranging in the values of x. So let us have a look at the figure once again. In the x direction, if I consider this y axis to be the reference and the complete length of the rod to be capital L, then I clearly know that on the left hand side of the of the axis, all the values have to be taken as negative. So this length will be actually read as minus L by 2, and this length will be read as plus L by 2. So this becomes the range of x for integration. In other words, what I'm saying is I have to take such similar small masses starting from minus L by 2, and I will keep on taking such small pieces individually, and I will carry on until I reach plus L by 2. And in this way, my complete integration will be made successful. So for dx, the range will be minus L by 2 to plus L by 2. This is how we change the limits. Initially, the limit was for mass, but as soon as the variable dx kicks in here, you have to replace it with something that relates to the variation of x. So x varies from minus L by 2 to plus L by 2 in such a way so that the complete mass of the rod will be covered eventually, starting from minus x by 2 to plus x by 2. So this is how we arrive at this expression. Now what we have in our hands is the overall value of I by y, which we desire for the rod, is given by the solution of this integration. Okay, so let us perform the integration. I'll do one thing. I will take out all the constant quantities outside. Rho is a constant, a is a constant. I take it outside. So what remains inside the integral is minus L by 2 to plus L by 2 x square dx. Now when you perform the integration completely, what you arrive at is this quantity. I'm not doing this integration because this is a very simple integration problem. You guys do it, and eventually you should arrive at this solution. I by y should be equal to rho a L cube by 12. This is what you should get. Okay. Now, please remember, or please recall by going back, that your capital M was already kept equal to rho AL. Now we are going to perform a small trick here. I will separate this result like this. Rho AL I will separate. Why am I separating it like this? Because I know that rho AL is equal to capital M. So that is why I am taking this quantity out of this result. Now what remains here? L square by 12. And now I will replace this quantity with M, and I will declare that for a rod which is thin, if you take the center of gravity and take a perpendicular axis passing through this and name it anything, you can name it as G or YY or ZZ, anything. If the complete mass of the rod is M, then the moment of inertia of a rod having mass M and length L about an axis perpendicular to the rod and passing through the center of gravity of the rod will always be m L square by 12. ये रिजल्ट आपको रट लेना है. ये आपके जिंदगी भर काम आने वाले रिजल्ट्स में से कुछ हैं. इनफैक्ट ये जितने भी डेरिवेशन इस वाले लेक्चर में मैं आपको बता रहा हूँ उसके एंड में जो रिजल्ट आ रहे हैं ये सभी आपको रटे हुए होने चाहिए टिल द डे यू डाई। इतना इंपॉर्टेंट है ये सारे, क्योंकि आप इंजीनियर्स हैं और आपके इंजीनियर का टैग जो है, आप भले ही प्रोफेशन में रहें चाहे नहीं रहें, एन इंजीनियर इज सपोज टू रिमेंबर वेरी बेसिक थिंग्स लाइक दिस। और ये आपके कम से कम इंजीनियरिंग के करियर में जो 8 सेमेस्टर हैं उनके अंदर तो ये सारे फॉर्मूले आपके टिप्स पे याद होने चाहिए आपको। सो स्टार्ट मेकिंग अ स्मॉल लिस्ट और टेबल ऑफ ऑल दिस फॉर्मूले अलोंग विद द डायग्राम्स। जैसे ये फिगर बना रखा है मैंने यहाँ पे, मास m है, रॉड बना रखा है, लेंथ l दे रखा है, तो ml²/12 इसकी मोमेंट ऑफ इनर्शिया होगी। दैट्स इट, यू रिमेंबर इट लाइक दैट। ओके, नाउ let us go to the next problem. The second solid object that we will be studying is a solid circular ring. So the next thing is a solid circular ring. So let me draw the figure here. I am trying to draw an isometric view. Since this is a solid ring, I am drawing two lines, and let us say this is the center of gravity of the ring. Yes, the center of the gravity of ring-like structures lies not on the body but in mid-air, where there is actually no material present. ऐसे जगह पर इस तरह के ऑब्जेक्ट्स का सेंटर ऑफ ग्रेविटी या सीजी आपको हवा में मिलेगा. So anyway, we want to find out the moment of inertia of the ring about this vertical centroidal axis. And let us say that the mean radius of the ring is capital R. This is given. So once again, I will take some small set of parameters that we are assuming that it is given to us. ये आपको अगर प्रॉब्लम में दें या नहीं दें, आपको ये पैरामीटर्स जैसे मैंने इनिशियली लिए थे वो पैरामीटर्स हर प्रॉब्लम के लिए लेने पड़ेंगे. फॉर एग्जांपल, इन दिस केस लेट अस से द एक्सिस इज z and I am saying that the overall mass of the ring is capital M. This is constant. The density of material of the ring is rho. It is again mass density, that means mass per unit volume. The mean radius of the ring is capital R, and the cross sectional area of the ring is capital A. Now, if you do not understand what this is, let me draw another simplified figure. So these are the four parameters that we are assuming to be constant and given to us. Whether it is given or not, you take it. Always remember to take it. Okay. So this A, where is this capital A? Let me explain it to you. Suppose if you have a ring like this, so assume that it is cut from this side, and this small piece is taken out. Now only a portion of the ring remains. So if I show you the isometric view, it is going to look somewhat like this. This. See, this much part of the ring I had removed. So if you cut this part out and if you look at the cross-sectional area, then this area is what I am calling as capital A. Now please remember, it is not necessary that the ring should have a circular cross-section area always. You can even have a ring like this, which has a rectangular cross-sectional area. See, this is also perfectly possible. Such a ring is also possible, where the cross-sectional area is rectangular or square or anything. Even a triangular cross sectional area is possible, or any type of cross sectional area is possible. But we are not bothered about the shape of the cross section. All that we are saying here is that the cross sectional area of the ring is constant, and we are taking it as capital A. That is all what we are saying. So given that, now you know what this capital A stands for. Okay. Now let us do the same steps that we followed in the previous derivation. Develop an expression for capital M. So you know that capital A is the cross sectional area, and if I multiply the cross sectional area with the complete circumference of the ring, then you know that I will get the volume of the ring. Now, what is the circumference of a ring whose mean radius is capital R? The circumference is 2 pi r. If I multiply this circumference with the cross sectional area A, I get the volume. And if I multiply the mass density of the ring with the volume of the ring, then I get the complete mass of the ring. So the expression for capital M becomes A into 2 pi r into rho. It does not matter in which order you write it, but this is the expression that we will remember as capital M. Now, again, according to the technique of the first principle that we have to apply here, what I'm going to do is I'm going to take a small elemental mass like this from the ring. This is the small elemental mass which I'm going to name as dm. And now let me expand it a little. If you look at the small elemental mass that I have cut out from the ring, it will look somewhat like this. Okay. So you will be able to see the cross section also. It will be slightly twisted because it is the part of a circular ring. It will have a small curve associated with it. So this is your dm. But since dm is very, very small, I can ignore this curvature and I will simply draw it as a small cylindrical piece. So now this cylindrical piece has a cross section exactly same as that of the big ring. And let us, for the sake of convenience, say that the length of this ring is small dl. Okay. Now, see, we are not taking it as dx or dy or anything because it is the length is measured in the circumferential direction, and because of that we cannot take it or treat it as dx or dy. But obviously if you want to take it as, just if you by force want to call it as dx or dy, it's your choice, but it's more logical to simply give it a name which is devoid of any directional quality, since it is not the this circumferential direction is neither x neither y. So that is why I am choosing to call this small length as dl. Now, for this small piece of mass dm, what is the length dl? What is the area? Capital A. So the volume is A into dl. Now what is the value of dm here? Dm is simply volume multiplied by density. So my expression for dm in this case is rho into A into dl, where A into dl is volume and rho is the mass density. So this is the expression for dm. Now I will just rub it out. Okay. Now we have the expression for capital M and we have the expression for small m. I will rub out the intermediate parts. Just like before. Please remember in the previous derivation also, we are doing the same same type of steps. See, we for the solid rod we started with a set of constant parameters that were known to us, m, rho, al, and then we declared the expression for capital M, found the expression for dm, and then we proceeded to find the small moment of inertia. So again, since the distance of this small mass element dm from the axis is nothing but our capital R, so I can say that the small moment of inertia di of this small mass about our desired zz axis would be simply dm into r square. Now substitute this value of dm in your expression of di. Di becomes rho a dl r square. Now, since I know the expression of di, what I'm going to do is find the value of the whole moment of inertia of the ring about the, sorry, this is the zz axis, and I'm going to take it as integral performed over the entire mass of the ring of di. And if I substitute the value of di in the integral from here, this becomes integral of rho a r square dl. Now see, initially di was a function of mass and the integration was supposed to be performed over the entire mass. But now the expression has a variable called L. And if you look at the ring, the length or this dl length is going to vary from 0 to all round the circumference. So the limit becomes 0 to the length of the circumference, that is 2 pi r. So I can conveniently replace this m and put the limits as 0 to 2 pi capital R. 0 to 2 pi r is the range of our variable L here. Okay. So once again, this is a very simple integration. You can clearly see that rho a r square, all these quantities are constant and they will come outside the integration. All that will remain inside the integration is dl. So I don't even have to leave it to you guys. I will just simply finish it off here. This will be rho a r square dl, or the integration of dl will become L, and putting the limits 0 to 2 pi r, we will get rho a r square into 2 pi r. That's it. Now once again, see, this is the value of I z z. So I will rearrange these things. R rho a r square into, okay, let us take it like that only. And now what I'm going to do is going to remind you of the value of m. M is a into rho into 2 pi r. So now we can isolate it here. A into rho into 2 pi r is m. So this quantity can also be written as m r square. So eventually we land up with a new formula. So whenever you have a ring like structure and you are asked what is the moment of inertia of the ring of mass m of mean radius capital R about the centroidal axis, then you simply say that Izz is mr square. Another important formula for you to remember. I am boxing the formulae that you have to eventually remember for the lifetime. आपको जिंदगी भर जो याद रखने के फॉर्मूले उन सबको बक्से में बंद कर रहा हूं मैं. So you know which formula have to be targeted. So if you happen to listen to this lecture, please note down all the box formulae separately in your notebook, and constantly from time to time keep on revising the formulae and try to remember it every time. Okay. So ring is also over. Now let us come to the next object, that is the disk. Solid circular disk. Now the solid circular disk can be drawn like this. Okay, 1 minute. I will just plug in my mobile. Okay, now we are again ready to go. Solid circular disc. So I will draw the solid circular disc like this. Obviously, I am drawing an isometric view. There is a thickness of the disc also. This is the center of the disc, and this is the vertical perpendicular centroidal axis passing through the disc. The overall radius of the disc is given as capital R. The thickness of the disc has to be taken. Let us say it is T. Whether it is given or not, you take it. Remember to take the thickness as T or H or anything, whatever parameter you like, but take a thickness. Now, once again, the constant parameters that they're assuming are capital M is the overall mass of the disk, rho is the mass density of the disk, capital R is the radius of the disk, again a constant, and the disk is of a constant thickness, small t. So these are the constant quantities that we will be taking for this derivation. Now, the first step, as in the previous two derivations you have seen, is to develop an expression for the capital M. What will be the total mass? So, by simple solid geometry, you should already be knowing that the mass of a solid circular disk of thickness T and radius R will be pi r square multiplied by T. This is the volume. Thickness multiplied by upper area. If you multiply it with density, this will give you the mass of the solid disk. So it is rho into pi r square T. Now what can you say about dm? This is the next step. But as you can see, we have not selected dm yet. So in the case of a disk, this is how you should consider your dm. You take a small ring like mass out of the disk. You cut it out in such a way so that a small ring like structure of thickness dr at a radius of small r is cut out. Now, if you are wondering what is the shape of the small dm, this looks like I have drawn two circles very close to each other on the top surface of the disk. But this is not actually how it is going to look. I will cut the disk. Suppose this is your disk. This is your disk. I will cut the disk like this, and I will take this piece out of the disk to show you how this small ring-like structure of mass dm is going to look. So this is your dm. So if I cut this piece out of the disk, this is going to look something like this. See, this is how your dm looks. So as you can see, this small dm that we are selecting, it has this thickness as dr, and this is the radius small r. Okay, at the location, small r denotes the location at which we have selected this small elemental mass. So if you take out this small elemental mass out of the disk, it will come out like a solid circular ring. This is how it is going to look like. It is going to look like a solid circular ring. This complete ring of inner dia small r and thickness dr is your dm. But you don't have to draw all these figures and prove or show to the examiner that you know or understand what dm is. Only this figure is sufficient. This main figure is sufficient. So if you draw a ring like structure here and declare that the thickness is dr at a distance of small r, and I am naming it as dm, then it should be sufficient. So let us remove all these extra drawings that we have made. We will go back to the main derivation here. So now the question still stands. What is the value of dm? dm should be equal to volume multiplied by rho. So what is the complete volume of the ring? This thickness, you should remember, it was taken by us as small t. So what is the area of this small rectangular cross section of the mass? This is T into dr. So T into dr is the cross sectional area. Now if I multiply this cross sectional area with the entire circumference of the ring, then I should be able to get the complete volume. So the complete volume V is nothing but T into dr cross sectional area multiplied by 2 pi into small r. So this is the complete volume. And if I multiply it with density, then this whole expression should be equal to the small mass of the elemental ring mass that I have selected here. So with this expression, we move on. Now, if dm is a mass which has a shape of a ring, now you see this dm is located, this is your dm, it is in the shape of a ring, and it has an radius of small r. Okay, and mass of the small ring is dm. So what will be the moment of inertia? We have already developed a standard equation for such quantities. For ring-like structures having mass m and radius r, the moment of inertia for an axis passing through the center will be mr square. So using this previously obtained value or obtained equation, I can simply say that for a ring-like structure, the di will be simply dm into r square. So I substitute this value of dm in di. So I get my di equal to t dr 2 pi r rho. This is dm, and finally this r square has to be written. So this is r square. So this is the expression for di. Now, what should I do to get the overall moment of inertia? If the small inertia of the mass is di, then what is the complete inertia of the entire disk? It would be obtained by integrating this di expression over the entire mass of the disk. So let me substitute all these values here. This becomes integral. I will rearrange it. See, this is 2 pi r, this is r square, so we can combine it. So I will write 2 pi r cube, then rho is there, then t is there, and finally I write dr. Now see, the integration variable is r here. So now you have to go back to your original figure and see. I have taken a ring-like element at a distance of small r. I start it with 0 value, then I take it at larger r value. Again, keep on increase the value of r so that in a stepwise manner I am moving outwards from the absolute center. So basically, if you understand this, you will know that I am changing the value of small r from 0 to capital R, which is the overall radius of the disk. So using this logic, since the variable of integration is r, and in order to complete the entire mass, you have to vary this small r from 0 to capital R. So this becomes the limit of integration. And now this problem becomes a simple problem of integration for you. So I will leave it to you at this point that izz is, take out all the constant quantities outside. That means 2 pi rho t. All these quantities will come out. Integration from 0 to r of what? R cube dr. You complete this integration on your own. This is a very simple integration now. Integration of r cube dr. Your answer should come out as izz is equal to m r square by 2. Obviously, you see that there is no capital M here. But after you get the result of this integration, you have to again go back to the value of M that you have developed here. Pi r square t into rho. See here. So using this expression and replacing it for capital M, you should be able to arrive at the final value of izz, mr square by 2. So once again, this is a result which has to be remembered by heart. And what is this result? For any disk, solid circular disk, if you get a centroidal axis like this, and the mass of the disk is capital M, radius of the disk is capital R, then the moment of inertia about this axis will always be mr square by 2. This is very important. You have to remember it by heart for the rest of your life. Okay, disk is complete. Now let us go to cylinder. So the next one is, I think this is the fourth derivation. Solid cylinder. Now you see, solid cylinder is nothing but a solid disk whose thickness is increased many times. A disk will look like this. Okay. And if I increase the height of this solid disk in the downward or upward direction, what I get is what we commonly call as a cylinder. So what I'm going to do is find the moment of inertia about this ZZ centroidal axis. Now, what are the parameters that are given or which you have to assume to be given? Capital M is the complete mass of the cylinder. Rho is the mass density of the cylinder. Capital R is the radius of the cylinder. And obviously, there is a height involved here, which is again a constant quantity and which we will take it as h. So these are the constant parameters that we start with. And as in all the previous derivations that we have done till now, The first step is to declare the expression for your capital M. Capital M, I am writing it without further explanation. I think this should be self-explanatory. Volume is pi r square h. This is the volume of a cylinder multiplied by density. This is the expression for capital M. Now, what is the shape of dm, or the small elemental volume that you are going to take? So let me just try to convert this cylinder in a 3D look-alike image. I'm going to take once again a disc-like structure as my dm here. This is going to be my dm. And since this disc-like structure has its thickness along the y direction, let me say that this very small thickness is dy. And let us say that the disk is at a height of y from the bottom side of the cylinder. So this is at a height of y from the bottom of the cylinder. So now what can I say about, now this whole disk has a mass of dm. Okay, so dm can be simply written as, now please note that since I have taken the cylinder, this cutout, or rather the disk, to be of exactly the same width as the cylinder, so the radius of this disk will also be capital R. So this should come out as pi r square. It is the area of the top surface of the disk multiplied by the thickness dy. This is the volume of the disk. And if I multiply it with mass density, this should be the small mass dm of this elemental disk. Now, I have dm here, I have capital M here. So I will create the small moment of inertia of the disk. Now, once again, what is the moment of inertia of this elemental disk? This is what we are asking. There is an elemental thickness disk of radius r. What is its moment of inertia about the same vertical axis? Since we have already developed this equation here, you see, if the mass of the disk is known, if the radius of the disk is known, then about the zz axis, any such disk will have mr square by 2 as the moment of inertia. So I can simply say that I know the formula for a disk-like structure, and that is the primary reason why I started with the dm in a disk-like shape. Okay, so you have to intelligently work like this. So dm is the mass of the disk, capital R is the radius of the disk. So what will be the value of di? The small moment of inertia of this disk will be dm into r square into half. That is half mr square. So half of dm into r square. This is my di. Now what am I going to do next? dm is already developed here. So I will substitute this dm in this expression of di. So my di will become, let us take down all the values, pi r square dy rho, pi r square dy rho, and then this r square is here, and then whole divided by 2 is there. So I will rearrange this. We get pi rho r raised to power 4 by 2 into dy. This is the expression that we get. Pi rho r raised to power 4 by 2 into dy. Yes, this is your di. Now again, Moving along the same lines, if di is known to me, how will I get the overall value of Iyy? Or let us see what is the name of this section, zz. So what is the overall value of Izz? This should be equal to the integral of your small moment of inertia over the entire mass. So if I put the value of di here, I will simply get integral pi rho r raised to power 4 by 2 into dy. Now see, y becomes the variable of integration. And go back to the figure and check what is the limit of y. See, this height is y. So as you see, if you want to cover the entire mass using such similar disks, you have to start from the bottom, take a small disk at the bottom, then a small disk above it, then another above it, and keep on going like this until you fill the complete cylinder with similar small disks to the complete height. So the range of your y variable becomes from 0 at the bottom to h at the complete height, small h. So all you have to do is simply replace this integration of m from 0 to small h of y. Now once again, this becomes a very simple problem of integration because pi rho r raised to power 4 by 2. This whole quantity is constant. So I will simply do it equal to pi rho r square, sorry, pi rho r raised to power 4 by 2. This is constant. I take it out. Integral 0 to h dy, that is pi rho r raised to power 4 by 2 into h. This is the value of your Izz. Now all you have to do is make a comparison with what was the expression for m here, pi r square h rho. So from this, I will separate pi r square h rho. This is your m. What remains in this expression? R square by 2. So this whole thing is already capital M. So eventually we once again get mr square by 2 or half mr square. Another result for you to remember. So this is something that you can remember like disk. If I have a disk of mass m and radius r, then the moment of inertia about the centroidal axis is mr square by 2. If instead of a disk, I have a cylinder of capital mass M and again radius r, then again the value of I is m r square by 2. And as we started, or as I stated in the beginning of the derivation, a cylinder is basically nothing but a disk with a large height. So even if you extended a little bit of your intuition, you could have guessed or you could have partially guessed that the expression for moment of inertia for both these quantities or both these solids will not be different at all. And hence, mr square by 2 is the moment of inertia of the cylinder also. And now, let us come to the next solid object, which is a sphere. Solid sphere. See, it's very difficult to draw a ball-like structure on a two-dimensional plane screen. But anyway, we will try to create a three-dimensional effect as good as possible. So the parameters that I'm taking is, let us say this is the center of the sphere. Just to show the center, I will draw the horizontal line like this, and I will draw a vertical line like this. So please assume that this is a sphere, not a circle. and this is the center of the sphere, which will be inside the volume. Okay, I am taking capital M as the complete mass of the sphere, and as previously in all the derivations we have taken, I am taking rho as the mass density. Let capital R be the constant radius of your sphere. So this is capital R. These are the parameters that are required for us in this derivation. Now, what we have to do is see what are the standard shapes we have already learned, or what are the standard shapes for which the formula of moment of inertia is already remembered by us. These are solid rod, a circular ring, a disc, a cylinder. So you should try to cut your small masses in such a way so that you get some standard shape always. So just imagine that I have a ball or a sphere with me, and I take a knife and start cutting slices of this ball like this. Now, if you can imagine even a little bit in your mind, you will clearly know or understand that if I take one such slice out of this collection, this is going to look like a disc to me, something like this. Okay, there will be a small curvature here, but since the thickness of this slice is very, very small, let us say dy. So I can say that essentially, if I cut this sphere into horizontal, infinite number of very, very thin slices or thin pieces like this, then each piece will be a disc-like structure having a very small thickness. But another thing is also known to you that each disk will have a different radius. See, this disk will have a large radius, this disk will have a small radius. So we will be having a lot of disks from top to bottom, having each of them having different radius. So this is the concept that we are going to go with for DM. Okay. So using this concept of a slice, and by slicing it in such a way, getting a disk, I'm going to make or take out a small disc-like shape at this height. So this small disc-like piece of volume becomes my DM. This becomes my DM. And I have taken this slice perfectly parallel to this line. Okay, although it might not look in the figure is a little bit distorted, or I'll do a little bit better job. I will just draw it again. This is capital R, and we don't know what is the radius of this slice that we are cutting because we have cut it at a random height. So let us call it as small r. The radius of this disk or the small element is small r. The thickness, since the thickness is associated with the y direction, let us call it as dy. And also let us say that this disk is at a height of say y distance from the central line of the sphere. And now with this information or with this logic, we can proceed. The first step is obviously to develop an expression for mass. What is the standard formula for volume of a sphere of radius r? You should all remember it. It is 4 upon 3 pi r cube. This is the standard equation of volume of a sphere. If you multiply it with mass density, you will get the expression for capital M. So this job is easily done. Now what you have to do is you have to develop an equation for dm. Again, if you look at the previous derivations, we are doing the same steps again and again. The only thing that changes is how your elemental shape dm looks like and what is the formula for it. That is the only thing that changes. Okay, anyway, you see that your disk, which is your dm, has a radius of r and a thickness of dy. So I will simply say that the surface area of the disk is pi small r square, and if I multiply this surface area with the thickness of the disk dy, I get the complete volume of the disk. And if I multiply it with the mass density, I get the required formula for dm. Okay, so dm is pi small r square dy into rho. Now, as was already discussed earlier, this small r is not a constant quantity. Okay, so there is a small problem here. This r will change if I change this vertical distance by. This is a perpendicular here. If I change this y, this small r is going to change. And my variable is dy. So this presence of small r is a little bit disturbing, or rather, it is going to create some problem in our integration. So what we should do is, we should try to eliminate this small r from the equation and try to bring in another term which should match with this dy. So either some constants should come into the equation or some y values should come into the equation. But small r is not an acceptable presence. Now look at this triangle that I created here inadvertently. This is capital R, this is small r, and this is the height y. And you obviously know that this is going to be a right angle triangle. So can I say from the configuration of this right angle triangle that my r square must be equal to capital R square minus y square? This is Pythagoras theorem applied in a different manner. Pythagoras theorem actually says that the square of hypotenuse must be equal to the square of height plus the square of base. So I just rearranged it a bit and quickly arrived at what I wanted here. So I can say that wherever I see r square, I can replace it with capital R square minus y square. So this intelligent transference of r to y has to be done. So look at the formula of dm. Now I'm going to use this in dm. So my dm becomes pi, and instead of small r square, I will put capital R square minus y square dy rho. Now this is my dm. Now I am very happy. Why? Because my variable is dy here, and all the remaining expressions in the figure are either constants or terms containing y itself. So now we are convenient and ready to go for integration. So with this, once again, dm is a disk-like structure. So this is the situation that we have here. We have the axis, let us say this is zz, this is the center of the sphere. Let us say I will draw a brief outline of the sphere like this. Our disk is located here. This disk has a radius of small r. This disk has a mass of dm. The axis is passing through the center of the disk. So everything said and done, we already know the standard formula of a disk like this is m r square by 2. So in this case, the mass of the disk is dm. So I will put dm into small r square by 2. So in short, I can say that if dm is the mass of the small disk, then the moment of inertia of the small mass di about the zz axis should be simply dm small r square by 2. Now this expression of dm can be substituted here, just like we have been doing till now. So my di will become pi capital R square minus y square into dy into rho. Now this small r square by 2 also will be appearing here. So let me put the by 2 here. But instead of small r square, why should I put again a small r square? Because this is a problematic figure here. I will again use capital R square minus y square for small r square. So instead of small r square, I will put again r square minus y square. So this is the entire expression for di. So let me rearrange it so that it does not look so long. Di is equal to pi capital R square minus y square the whole square, because r square minus y square is appearing twice in the product. So this becomes whole square multiplied by rho into dy whole divided by 2. This is the expression for di. Now if I get the expression for di, as always or as usual, the complete moment of inertia of the sphere will be the integral of di performed over the entire mass of the sphere. I will substitute this expression of di here. So this becomes integral of pi r square minus y square the whole square rho dy by 2. Now see, the variable is y. Now let us go back to the figure of our sphere and see, this is your vertical height y. And in order to fill the complete sphere with such disks, you have to start with the bottom disk, then put a disk above it, then put a disk above it, and so on. You keep on filling the sphere with multiple disks. So this process actually is happening from minus r distance at the bottom of this axis to plus r distance above this axis. See, this entire length has to be covered, this entire length has to be covered. So the limits of your integration actually become minus capital R to plus capital R. This is what you have. And although I can show you the complete steps for integration, this is the end of the problem. Now all you have to do is perform your simple integration. You can take the constant quantities outside. Pi rho by 2 can be taken outside. Integration minus r to plus r square minus y square dy. This is the integration that you have to perform. And I think you are perfectly capable of doing this. You simply expand this. Okay, this is whole square. I will write it a little bit more clearly. Izz should eventually be the result of integration of pi into rho by 2 taken outside, integral minus r to plus r of r square minus y square the whole square dy. Now you solve this integration. All you have to do is you square this term and break it into individual quantities. You know the formula of a minus b the whole square. Use that formula here and expand this and solve each term by integration. Add it, apply the limits, and eventually your answer should come out to be equal to, it should be, just let me see, Izz should be equal to uh, 8 by 15 r raised to power 5 into rho pi. This should be the expression. But again, as we have been doing till now, you go back to the reference value of your capital M. Capital M is 4 upon 3 pi r cube rho. So we will bring it here. We know that capital M is 4 upon 3 pi r cube rho. So we can extract it from here. So Izz can be written as 4 upon 3 pi r cube rho. I have taken it out. Now what is the thing that remains after taking this out? That is 2 by 5 r square. So this whole thing is capital M. So your Izz becomes 2 by 5 m r square. Another standard formula for you to remember by heart. So for a sphere of mass m, if somebody gives you a centroidal axis and the radius of the sphere is r, and if somebody asks you what is the moment of inertia of a sphere about its centroidal axis, it is 2 by 5 mr square. Remember it by heart. And now we finally come to the last figure or the last solid, that is solid circular cone. Everybody knows how a cone looks like. So we are taking a cone with height h and the base radius as capital R. Once again, we assume capital M to be the total mass of the cone, rho to be the mass density of the cone, and obviously two parameters are already given in the geometry. Height is h and base radius is r. So these are the constant quantities we start with. Now, just like what we did in the previous derivations, capital M will be equal to volume into density. What is the standard volume formula for volume of a cone with height h and radius r? It is 1 upon 3 pi r square h. These formula you should know. These are 10th class formula. Okay. So this is volume. You multiply it with density. So this is the expression for M. And now once again, what will be the shape of dm which is convenient for you to take? You should take it as a small slice in the shape of a disk at some random height here. Take this slice of the disk in such a way so that it falls parallel to the base circle. Okay. Now, since the cone is a tapering type of solid, so obviously, depending on what height you cut the disk from. So let us say you cut the disk at a height of y from the base, and the thickness, very small thickness of the disk is dy. So let us say that at this height, the radius of the disk obtained is small r. We don't know this small r. This is not a constant parameter. If you cut it at this height, the small r will be different. If you cut it at this height, the small r will be different. So randomly we have taken a small slice to be called as dm. So this is your dm. The mass of the disk is dm. It has a radius of small r and it has been cut at a height of y. The thickness of the disk is dy. So immediately we can go about developing the expression for dm, which will be the volume of the thin disk. So it is pi r square into dy. This is volume. Now you multiply it with density. This becomes mass. So dm is pi r square dy into rho. Now, once again, the same dilemma is being faced by us because small r is not compatible with your variable y here, because small r is not a constant, it will keep on varying with respect to y. So what we have to do next is we have to somehow find a geometric relation which will replace this small r from the equation and bring either some constant quantities or y in the equation. Now look at this configuration. This is the overall height of the cone. This is capital R. This is a hypotenuse. This is 90-degree here. This is small r here. So if I extract this two-dimensional geometry from this solid, what I get is two similar triangles. This is capital R. This whole height is small h. At a height of y, we took a parallel line, and at this position, this is small r. Look at this figure again. This is what we get from the geometry of the cone. Okay. So I can say that this smaller triangle is similar to this overall larger triangle. So in a similar triangle, we always have some relationships of ratios like this. So this is 90 here, this is 90 here. Okay. So now what we can declare is, what is this height of the smaller triangle? This has to be h minus y. So for the smaller triangle, if I take the ratio of perpendicular to base, I get h minus y upon small r. And for the larger triangle also, if I take the ratio of perpendicular to base, this comes out as h upon capital R. And since these two triangles, the smaller triangle and the overall larger triangle are similar to each other, then these ratios must be equal to each other. And this is from where we get a replacement for the undesired variable r. So if I rearrange these quantities in this equation, I get small r is capital R by h into h minus y, capital R by h into h minus y. This quantity is the replacement of small r. And now see, r is a constant, h is a constant, h is a constant, and only the desirable variable y is present, which matches with the variable of integration. So I will make this replacement. Instead of small r, which is appearing here, I will put this expression. So eventually, my dm becomes pi r by h minus y square, because there is pi r square. See, it is pi r square, and the remaining dy and rho. I will simplify it a little bit. Dm becomes pi capital R square upon small h square, h minus y the whole square, rho dy. This is the expression for dm. And once again, dm is the mass of this disk. So if I want to find out di, I will simply have to apply the formula for inertia of a solid circular disk. And since this has a mass of dm and a radius of small r, so di can be simply put as half of dm r square. Why half of dm r square? Because the formula for any disk of mass m and radius r, the moment of inertia I is m r square by 2. In this case, this capital M is dm, this capital R is small r, and the half will come as it is. So this is the expression for your dm, sorry, di. So this small r is coming once again. So if I want to reproduce this expression of di, it will be half of, I will bring dm. Dm is this whole quantity. See, this whole quantity is dm. So I will bring it here. Pi r square upon h square into h minus y square into rho into dy. This is complete dm, and now r square will also come. R square. Now see, we have very painstakingly removed the variable r, removed variable r, and still r square is coming. So what I will do is I will simply replace this r square also with this expression, the replacement expression. So instead of r square, what I am going to write is again capital R square by h square into h minus y the whole square. So this is the complete expression for di. I will simplify it again a little bit. Your di becomes half of pi r raised to power 4 upon h raised to power 4 h minus y whole raised to power 4 into rho dy. See, I have combined this r square by h square here, and I have combined h minus y whole square with this h minus y whole square. So this is the expression that you get, di. Now again proceeding along the same lines, to get the complete moment of inertia, you have to integrate this expression of di over the entire mass. In other words, if I use the variable dy, so half of pi r raised to power 4 upon h raised to power 4 h minus y whole raised to power 4 into rho dy. Now, since my variable of integration is y here, so I will go back to the figure of the cone and see from where to where y has to vary. So y has to vary from the bottom of the cone to the top of the cone in order to cover the complete volume of the cone. So the limit of integration becomes 0 to small h. So this I'm going to apply here, 0 to small h. Now you can take out all the constant quantities outside. So your overall moment of inertia is half pi capital R to power 4 by h to power 4. All these are constant quantities. Rho is constant. The only thing that will remain inside the integration is h minus y whole raised to power 4 dy. I will solve this for you. Half of pi r raised to power 4 upon h raised to power 4 into rho. This can be put as h minus y with a negative sign, because in the expression of h minus y, y has a negative sign and the variable of integration is not h, it is y, with the limits of 0 to h. This is the, sorry, power of 5 will be there, divided by 5 will be there. This is the correct expression or the correct solution of integration. Now we will continue to solve it. I is equal to half pi r raised to power 4 by h raised to power 4 into rho. Now if I solve this, in place of y I have to first put h. So h minus h becomes 0. So this is 0 minus, now in place of y I will put this 0. Then it becomes simply h minus 0 raised to power 5. So that means minus, this minus sign will obviously come here, h raised to power 5 by 5 This is how you solve it. So eventually what I get is I is equal to, this is 2. So 1 by 10 pi r raised to power 4 upon h raised to power 4 into rho into h raised to power 5. So h raised to power 4 will cancel out with h raised to power 4. What remains is pi r raised to power 4 h into rho by 10. So this is the expression for I. Now let us do the last step, that is replacement of some quantities with capital M. So capital M in our case was 1 upon 3 pi r square h rho. Let us bring this into picture. So I is this and M is 1 upon 3 pi r square h rho. So for convenience, what I am going to do is I am going to say that 3m is equal to pi r square h rho. So in the expression of your moment of inertia I, if I can extract pi r square h rho, I will replace it with 3m. Okay, so I can see pi, I can take out r square from r raised to power 4, h is there, rho is there. So I will, after extraction, what remains is I will say this is pi r square h rho. I take it out. So what remains? Pi is gone, r square is gone. So r square remains, h is gone, rho is gone. So this is r square by 10. Now I know that pi r square h rho has to be replaced with 3m. So here I will write it as this expression will be 3m. So this eventually becomes equal to 3m r square upon 10. 3 by 10 mr square, and this is the result which you have to remember. This is 3 by 10 m r square. One interesting thing you can note, that small h is completely eliminated from the picture. There is no role of small h now. So if somebody gives you a cone of mass capital M and base radius capital R. So now you see, according to the final formula that you achieve, whatever the height of the cone is, it is totally immaterial. The only thing that are required are the overall mass of the cone and the base radius of the cone. That's all. So it will be 3 upon 10 mr square. So we have covered all these topics. We have covered for a solid rod, for a solid ring, for a solid disc, cylinder, sphere, and cone. So make sure that after looking at this video, you take one solid object every day to practice. One day you take a disc, one day you take sphere, one day you take the cone, and try to take a rough copy, take a pencil or a pen, and try to find out whether you can do the complete derivation without any external help. So keep up the practice and best of luck. So we will stop the lecture here.